me try this again. I'm recording this after school because it didn't go well, or I kept recording 4 hours worth from second period on. So, first, the notes have been updated, so if you got the notes earlier, then you might look at the new notes that I posted on my website. Here it goes. That's what this will follow. All right. So, the idea of today is set 138, conditional convergence. We talked earlier about absolute convergence, and absolute convergence is when an alternating series converges even without the alternating negative that helps it converge, then that's called absolute convergence. So if you take out the negative by taking absolute value, and the series that results converges, then you say the alternating series converges absolutely. Today we'll talk conditionally. If you run it without the negative and it diverges, which is to say it does not converge absolutely, but with the negative it does converge, then that's called conditional convergence. If the negative one that alternates helps it converge, then it's conditional convergence. It's also worth noting that if a series converges conditionally, then it converges. And if it converges absolutely, it converges. So by proving absolute or conditional convergence, you're proving convergence. Now, how to prove conditional convergence? That's the meat of the problems you'll see. How do you prove it? It's really pretty straightforward. It's just 3 conditions. This is also called the Leibniz test in some textbooks. All right? You can prove an alternating series converges by, first of all, showing that it is an alternating series. This idea only applies to alternating series, not positive term series or all negative term series, or series that don't alternate in a one-to-one switching kind of form, like cosine or sine line. All right. The second thing is that the terms go to 0, which is to say that the terms pass the divergence theorem, which we should always be checking anyway. And last but not least, the terms steadily decrease. If that happens, then as you add terms, say it starts off with one term and it's maybe this big. Let's say the first term was negative. Then the second term should be positive, and so when you add it to the first term, I guess that would be, let's say the first term was positive. The second term was negative. That would bring the overall sum down when I sum the first 2 terms. Now the third term would be now adding a positive, but if the terms are decreasing, then it would be less than the original distance. And then when the next term is negative is added, it's less of a distance than earlier. And so you're gradually adding less and less, and you start to head in towards the limit. All right? That's the idea of conditional convergence. So let's show you what this looks like here. Typical question is, given this series, this is supposed to be to the end, does this series converge absolutely, conditionally, or does it diverge? First thing you're going to do, like always, is check the divergence theorem. You'd say to the reader, hey, the terms do go to 0, so it has a chance. I'll investigate further. Now, if that's not satisfied, just like always, call it good. If the limit of the terms is not 0, then it diverges, and you're done. That's still true for alternating series as well. If the terms do go to 0, check absolute convergence next. You check absolute convergence first to see if you can do it without the negative. So that we've been doing before. If I took the absolute value of the series, it becomes 1 over n to the half, which diverges. P series. P equal 1/2 less than or equal to 1. Right? So it does not converge absolutely. The alternating series does not converge absolutely. That's one possibility down. Now let's talk about conditional, which is today's new stuff. All right. First of all, you can do this in a check kind of way. Is it alternating? Well, yes. -1 to a power would alternate back and forth. Second, do the terms go to 0? Now we already got that in our record, so I don't know if we need to put it again, but we'll say we met the second condition. The third condition. Now, if I were to, first of all, don't worry about taking the negative in there. When we go to show the terms are decreasing, we're looking at the positives only. And so what we're going to do here is show that the terms are decreasing by stating that the n plus 1th term, which is n plus 1 square rooted, is less than 1 over root n. I think you'll agree that's true. So it is true that the n plus 1th term is less than, and that's true for all n's that are positive. So the terms are decreasing all stages. They're constantly decreasing. 1/3 is less than the square root of 1/4, the square less than the square root of 1/5, and so on. So we can conclude then that the alternating series converges conditionally. Right? It cannot converge absolutely and conditionally. If you look back at the definition of conditional, conditional is when it doesn't converge absolutely. The absolute value diverges, but with the alternating negative, it converges. All right, so there's no overlap between absolute and conditional. All right, going on to another example here. Does the series given here converge absolutely, conditionally, or diverge? Well, following the same steps, do the terms go to 0? And yes, they do. It has a chance. Absolute value or absolute convergence is the series 1 over n plus 2. We could do this a little quicker and say, we could just say this diverges by comparison to 1 over n, the harmonic series. So the alternating series does not converge absolutely. Now, you might ask, is that thorough enough? Is that to prove, or do I actually need to run a comparison test, the limit comparison test, or the direct comparison test? And I feel like that is sufficient here. I guess I need to get clear in my mind exactly what I need to see, but for now, that to me is thorough, and I understand where you're coming from, and you could prove it if push came to shove. Last but not least, now let's talk conditional. For conditional convergence, it is true that it is alternating. It is true that the terms go to 0, which is the second condition. And the third condition is the n plus 1th term would actually be n plus 1 plus 2. That's the nth term when we replace n with n plus 1. And that is less than the nth term, which is in the series itself, n plus 2. So it is the case that the terms decrease. Therefore, we can conclude the alternating series converges conditionally. Okay, that's what we're looking at. Try these on your own. Pause it for a second, and when you're done, play the recording and we'll get going. Okay, so here we go. This first one, I would say that one of the terms is 0, so it has a chance. If we looked at the absolute value of the series, it becomes 1 over 3 to the n plus 1. And I'm feeling that will converge by comparison to a geometric, and therefore the alternating series will converge absolutely is where we're headed. So you could, if you were to compare to 1 over 3 to the n, maybe by limit comparison test, 1 over 3 to the n plus 1 over 1 over 3 to the n equals 1. And so because because that limit is between 1 and infinity, both converge or both diverge. 1 over 3 to the n converges because it's geometric with an r less than 1, and r equal to 1/3, which is less than 1. So we can conclude, therefore, that the alternating series converges absolutely. We don't have to bother then going on to conditional. If it converges absolutely, we're done. Okay? The next one. Terms go to 0. If you take the absolute value of the terms, comes 1 over root n plus 1, which diverges by comparison to 1 over root n, which is a p-series. So what about conditional? Well, so the series does not, the alternating series does converge absolutely. What about conditional? Well, it is an alternating series. The limit of the terms is 0, as we've already stated. And as far as the nth term, the n plus 1th term is 1 over root n plus 2, and that is less than 1 over root n plus 1, which implies that the n plus 1th term is less than the nth term. So we can conclude this series, the alternating series, converges conditional. Right? We did one like the third one a couple of days ago. I think you'll agree that while cosine stays relatively small, 3 to the n gets large, and so the terms go to 0. In terms of the absolute value, that's gold there. We're going to prove convergence of this by comparison, but it has to be direct comparison. If I know that cosine of this, by the way, is the same as cosine of n over 3 to the n, if you like. Now I know cosine of n's absolute value is less than or equal to 1, and therefore the cosine of n divided by 3 over n is less than or equal to 1 over 3 to the n. And the series, therefore, is less than the series over 3 to the n, which converges. Let me say this well. Because the series of absolute value of cosine of n over 3 to the n is less than the series 1 over 3 to the n, and 1 over 3 to the n converges, geometric, r equals 1/3 less than 1. The series cosine over n cubed converges, and the given series converges absolutely. All right. Also notice, if you tried to do conditional convergence on that, cosine of n, yeah, it does bounce around signs, but it doesn't alternate. It goes kind of positive, negative, negative, and then it goes positive and then negative. It's not a converging or a alternating series, so you couldn't even use the Leibniz test on it. This guy, the terms is not 0. Don't say it's infinity because it bounces back and forth. I guess you could say it's positive or negative infinity, but it's really just oscillating back and forth and definitely not going to 0. So, gosh, we're done. This diverges. All right. The next two are a little more challenging. They ask you to use or remind you, review a little bit of series knowledge, and that sometimes series are a little more complicated than just a straightforward summation. So look at the first one. you notice, it's kind of weird in that it alternates later. This should be negative. Sorry, I changed that to negative. But at the front it doesn't. And those terms on the front aren't even a part of the pattern. Well, you can deal with that by just removing them from the pattern and saying, hey, the summation starts there, maybe at n equal 3. You could actually say this is 1 over n and start it at 3, or you could say it starts at 1 and call it 1 over n plus 2. Either one could start it at 0 and say it's 1 over n plus 3. Now, once you have this, though, nailed down, then you can worry about how do I make the alternating negative. If I wanted to start positive, then I wouldn't say negative 1 to the n, because if n starts at 3, that would be negative 1 to the 3. That would be negative. So it would have to be something like negative 1 to the n plus 1 or minus 1 to make that first term positive, right? Now that I've got the series a little more clean, then I can go about my normal business. I say the terms of that series do go to 0, has a chance. I could prove that the series does not converge absolutely because the series with the absolute value, which would be 1 over n, diverges on it. So that leads me to prove conditional. Well, it's an alternating series. Check. The terms do go to 0. Still not sure. Do I really need to say that again? It's really my work already been stated, so it feels like that's pretty good, but I am just going through the checklist. And then last but not least, 1 over n plus 1 is less than 1 over n, which implies the absolute value base of n plus 1 is less than base of n. Terms are decreasing in value. If the terms are decreasing in value, absolute value to 0, then this series must converge. Condition. All right. And last but not least, this one's a humdinger. Give it a second look and see if you see what's going on here. It's not easy. This requires some experience in having seen things a few times. See, hopefully you see that there's actually two things going on. One, there's an exponent and a 2 thing, but it seems like it's every other term. These guys are 1 over 2 to a power, and they seem to be alternating. But the other guys are more like a harmonic kind of alternating thing. So what do? Well, let's split them. Let's split that into the harmonic. 1 minus a half, that's a third. And the exponential, 1 over 2 minus 1 over 2 squared plus 1 over 2 cubed. And deal with those separately. And this is the series 1 over n. If I start with 1 over n, then that means the index must start at 1, and so that would be negative 1 to the, I want to start positive, so I'm going to go at plus 1. I'll verify that works out 1. I'd get negative 1 squared over 1, which seems good. When n is 2, I get negative 1 cubed, which is negative over 2. That seems like it's working. All right, the next series is 1 over 2 to the n, starting at n equal 1, but with the alternating negative, the top maybe should be negative 1 to the, this one starts positive, so I need to probably bump that up, right? After that, you could look at each problem individually and tackle convergence or divergence. This guy, you could prove converges. In the interest of time, I'll just give you the anticipation. The terms go to 0, but it doesn't converge absolutely, harmonic. We can prove, and it has been proven, that that it's converging conditionally. The terms decrease in value, it's alternating, and the limit of the terms is 0. So you can prove conditional convergence there. Right? This one, even if you took out the negative 1, it's still exponential. 1 over 2 to the n converges absolutely. Now, if the question, honestly, I had this question is, does it converge absolutely or conditionally? And then I was confused myself because I'm not sure what to say. Does it converge conditionally or absolutely? So I changed the question to just, does it converge? And the answer is yes. If this series converges conditionally and that series converges absolutely, they both have finite sums, and so the sum of two converging series must be converging. So the original series converges. And let's not go conditional or absolute. Let's just say it converges, shall we? That's pretty much it. We didn't get to this one in class, but in the interest of time, because this is going a little faster now, I'm going to do it here. So if you think about what x's would make this converge and which wouldn't. If you did, let's think of some interesting things. If x is 2, then we'd get something like, sorry, I zoomed out. 0 to the n over n, which is 0. That seems like it converges. Let's go to x equals 3. 3 would be 1 to the n over n. That's harmonic. That diverges. What about the other side of 2, like x equals 1? Well, that's negative 1 to the n over n. That's conditional convergence we've seen. All right. So let's say, what else would be interesting? Maybe we should go a little bigger. What about x equals 4? If x equals 4, then we're talking 2 to the n over n. That fails divergence theorem, so that diverges. Same with below 1. If I did 0, that's negative 2 to the n over n. That fails divergence theorem. So we need to make sure that the exponential is small, so it doesn't dominate. So think of it more like a geometric kind of thing. X minus 2 needs to be less, in that 1 to 3 range. X minus 2 has to be between negative 1 and 1, which means x has to be between 1 and 3. And then at the endpoints themselves, we know that while 1 did work conditional convergence because we had a negative, then 3 didn't. So it feels like it converges for x's between 1 and 3 equal to 1, but not equal to 3. Then the other part, you can bypass that. You're good. All right. The only other thing is we got 2 questions on the homework, but number 8 is a bit of a humdinger. So if you skip number 8, that's okay. We'll talk about it later. Have a good day.